So good morning. We will continue our discussion on the interaction between atoms, or more generally matter, with light. Matter and light basically form the whole universe, what we have in the whole universe. So this is a big topic by itself. We developed the first order time-dependent perturbation theory, and then we already looked at some consequences. So very simple formula, but there are many common sense consequences. For example, we saw how the selection rules come out. We also saw how the selection on the right frequency, the incident light h bar omega must hit the energy difference of two levels in an atom. So we have derived rather successfully two formulas. One has to do with stimulated absorption rate, that is the probability that a transition occurs per unit time for an atom. At the same time, using one formula, we also got the stimulated emission rate. So let us recap what those formulas are, and then we will move on to find a way to get at a formula for this spontaneous emission. So last time we derived using the time-dependent perturbation theory. This equation highlighted on this page. This is absorption from a state 1, which is lower in energy, to a state 2. It is stimulated absorption because explicitly it depends on how strong the incident light at that particular frequency, omega 21, which is the energy difference divided by h bar. So here implicitly already two things here. The frequency must be right. It is stimulated because if this is 0, you have Do you hear me? All right, there's a connection problem. Okay, sorry about that. Suddenly there's a connection problem. So let me continue. So I'm back. So there is an integral here that we already saw. It is giving us the selection rules. Similarly, we also obtained the stimulated emission formula, that is the per atom per unit time. That is called the transition rate. Again, it is stimulated because there is a factor of how strong the light at that right frequency is about. And also there's the same integral, but this is initial, final, final, initial, what this 1 and 2 interchange, because in emission, you need the initial one to be higher than the final one. But since we are looking at the absolute value square of this integral, R21, this one will be the same as this integral square. So let us summarize. Using our time-dependent perturbation theory, we already got this very insightful result. Given the same condition, that is to say, you have two levels, some atoms, you have a collection of atoms, some atoms may be up there, some atoms may be down there, and then under the same intensity of light, you have this transition rate of absorption being the same as the transition rate for stimulated emission. Now take this answer with you. We have to wind back the clock to a few years before quantum mechanics was established. Namely, we will go back to 1916, 1917, when Einstein did some work on blackbody radiation formula, and somehow he also at the end concluded this relationship. So this is the topic that we want to discuss today. Why we want to do that? The reason is that we have this stimulated absorption formula and stimulated emission formula. But there is a process that is rather embarrassing for Schrödinger quantum mechanics, which is the phenomena of spontaneous emission. We know well that if an atom is in an excited state, you don't do anything to it, it will not stay there. It will decay to a lower energy state, for example, by emitting a photon. So that is spontaneous emission. You don't need to do anything about it. However, with our perturbation theory, every time when we invoke the perturbation theory, we need some perturbation. We need something else to disturb the atom. But for spontaneous emission, there's nothing, apparently nothing, to disturb the atom. Therefore, we cannot do anything more within Schrödinger quantum mechanics to explore spontaneous emission. The way in quantum mechanics to do it is we have to do quantum field theory. That is to say, we have to quantize the EM field first, and then work with the atom and the quantized field, and then we realize the vacuum. You don't do anything about it, the vacuum is not nothing. But this is beyond the scope of our course. So we find a detour, 一個轉彎啊，揾條路走啊，就呢條路拐過去. So, and it is a very insightful story that we went back, we will go back in time to Einstein's time. So he developed a way to get at Planck's blackbody formula, in which he actually proposed a new phenomena at his time called stimulated emission. Then he could give us a relationship between spontaneous emission and stimulated emission. But we know the formula for stimulated emission, therefore, using his answer, we can get at the formula for spontaneous emission. So it is killing two birds with one stone. First, we can look into how Einstein argued and used statistical physics to get at the Planck's formula. Secondly, we can get a formula without for spontaneous emission without doing anything more. So that is why we have this particular section here. So it is about Einstein's so-called A and B coefficients. That is a very famous piece of work. It was 1917 published. So 1916 when he worked on this piece of work. And you know, he was already rather famous at that time with special relativity and also general relativity in 1915. So what did he want to do? Just like every famous physicist at that time, all of them tried to derive the Planck's formula using their own way. So the story goes, 1900, Planck wrote down a blackbody formula that fits the experimental curve very well. And then he tried to understand why his formula worked. Then he realized that oscillators, he was referring to the oscillator of matter, the atoms, must have discrete energies instead of h mu or h bar omega. So that is how the whole quantum era started. And we have Boltzmann from 1880 to 1900 developing statistical physics together with Gibbs. And Einstein actually stepped in 1905, photoelectric effect. So he proposed that photon light is composed of a stream of quanta, and each unit of energy is h nu or h bar omega. And then we also have Bohr, 1913, his model of the hydrogen atom, whereby there are stationary orbits, but in order to go with the spectrum, this stationary orbit could have transitions between one orbit to the other. The energy difference will be given out according to Einstein's photon. So, you know, the development is rather logical in time. And then we had Einstein, 1916, re-deriving Planck's formula. And another very important development was in 1924, where Bose also re-derived the Planck's formula with the idea like there's a gas or photon. And at the end, Einstein got the paper, and then he further developed the Bose idea to treat real boson atoms. And therefore, we have something called the Bose-Einstein distribution in statistical physics. So this blackbody radiation formula problem is a very challenging one, of course, that attracted all the big names. So let us look at what Einstein did. So what he wanted to do is to derive Planck's formula. This is the usual form when you first encounter Planck's formula, this one. I intentionally break up the whole formula into 3 factors. So there is a factor like this, and then there's a HF. I hope that you know this is an energy of a photon. And then for those who are doing statistical physics course, this is related to the Bose-Einstein distribution. More importantly, what is this quantity referring to? It is the energy per unit volume of the cavity due to EM waves that lies in the frequency range F to F plus DF, when this whole system, the EM wave and the body, the cavity usually, they are at equilibrium at a temperature T. Therefore, you have the KT here. All right. Now, for us, we have been using omega for our frequency, angular frequency. Therefore, I first change the variable from HF to H bar omega. Therefore, after you do this, this is the formula of blackbody Planck's formula. So we have a constant, a group of constants in front with omega square, and then we have H bar omega. Therefore, you see there's an omega cube factor. We have something like the Bose-Einstein distribution, and then this carries the same meaning, apart from now it's from omega to omega plus d omega. So 1916, Einstein wanted to find a way to derive this formula using statistical physics. Nowadays, we are using this formula day in and day out. For example, if you use this formula to plot out two temperatures, you fix temperature to T1, T2. So the whole distribution in frequency, the lower one is of lower energy, the higher one is higher energy. If you integrate this whole thing over frequency, this area under the curve goes like T to the fourth power. And that is called the Stefan-Boltzmann law in EM radiation theory. And now we are using thermometers every day. So when you use your forehead to let the thermometer plot your temperature, basically, I think they are using this formula, maybe looking for the peak where it is representative of your temperature. And there are three factors already I indicated. For those who, if you are doing Professor Gore's course, have you learned density of states? Did you do that? Hello? Have you? Not yet. Oh, just midterm yesterday. Okay. Now, later on, I'm sure you will see something that is called density of states, probably in a gas of electron. But if you follow the idea, it is the same thing for the first term. It is the density of EM moles. It is like you have a box. Think about a metal box to N. You are fitting EM waves. So the longest wavelength, the second one, the third one, so it's like particle in a box in quantum mechanics. And then after you do a lot of this, you ask from omega to omega plus d omega, how many waves can you fit in? You will see this is the answer times d omega. Okay, so this is the number of moles or density of states. And this is photon energy. And therefore, this can be think about as a temperature dependent excitation of the number of photons. So this is the temperature, at a certain temperature, how much this particular mole is excited. Now, don't worry about it. You will learn it in the thermal and statistics course. This is optional. But as we are looking at the formula, why not mention some physics about it so that you can make connection to your other course. So we have Bohr, we have Einstein. So let's start with Einstein's idea. So basically the idea is the following. You have a cavity full of atoms. Inside the cavity, there are EM waves. the EM waves are being absorbed and emitted continuously by the atoms. They interact, that's the whole point. The atoms and the EM wave interact, they exchange energy. Therefore, they could achieve equilibrium and arrive at the same temperature T. So we have a temperature T to characterize this system consisting of atoms and EM waves. And we want to look into the EM waves properties after this atom EM wave system achieved equilibrium. So that is the very standard statistical mechanics or statistical physics idea. To make the whole thing simpler, let's consider a particular atom with two states. So two level atoms again. So we have E1, E2. The omega between them is E1 minus E2 divided by H bar. And now it is interacting with a EM wave background, and this omega will have an intensity in the EM wave given by U of omega. This is exactly the U of omega in the formula that we derived, all right? But because we are also doing statistical mechanics a little bit, I also include the temperature here. But basically, when we see U of omega, it is the same thing as we used it in our previous formulas. We only need one small piece of thermophysics. This is the Boltzmann factor. That's it. What does it say? It says the following. So I have a total number of N atoms. And they form two groups. It is a dynamical equilibrium situation. And one of them are the atoms in state 1. And two of them are the atoms in state 2. So I'm thinking about this. There are N1 atoms in this state and 2 atoms in this state. Because it is in thermal equilibrium at a temperature T, one, perhaps the most important idea in statistical physics is the following. The number of atoms in a state of energy E is proportional to exponential minus that energy divided by KT. There may be a constant in front, but it doesn't matter. We have 2 levels. We are looking for the ratio. So whatever constant in front, they will cancel off. So I only need to use this particular idea. Therefore, the number in state 2 will be proportional to this factor. The number in the lower state N1 is also proportional to this number. If there is a prefactor, they appear here, they cancel off. So I don't need to even worry about that. And therefore, we have the only piece of thermophysics we needed. The ratio N2 over N1 is given by this exponential minus the energy difference, which is positive, E2 minus E1 divided by KT. Or because we have already defined this divided by H bar is omega or omega 2,1. So it is H bar omega. All right. So N2 over N1 is this. We will be using it in the derivation. And that is as much statistical physics or thermal physics we are using here, nothing more. But there's one important, there is some important observation. N2 over N1 is this, and this is positive, all right? Therefore, you see, there's always there are always more atoms in the lower state than in the upper state where the system is in thermal equilibrium. All right. Now, you must have used some laser before, and you must have heard about laser physics before. For a system to have lasing property, you need more atoms in the higher state than in the lower state. But using thermal physics at equilibrium, we already see from this little piece of thermal physics that you cannot do it at equilibrium by temperature. So you heat up the system, you are moving more atoms up there, but you can never get at more atoms at a higher level than lower level. So don't be too naive, okay? As CUHK student, you cannot use temperature to put more atoms in a higher level than in a low level. That is dead wrong, okay? Don't ever think about it. It is because of this Boltzmann factor. So now Einstein got to work. Again, let me remind you, he was trying to derive this, okay? And then he found that he need to propose one new, at that time new, phenomena. So therefore, he needed 3 processes instead of the 2 well-known processes at that time. The processes are stimulated absorption, that's natural. When you have atoms down here, you have some stimulation at the right frequency, it will absorb. Well, that was known in the 19th century. You have all this spectrum of atoms. This is also well known, spontaneous emission. You excite some atoms, you just wait, they will come down by themselves. So it is spontaneous emission. So these 2 are kind of well-known processes at Einstein's time and before. I believe he must have tried the 2 processes alone, and he found he couldn't get the Planck's formula. Namely, let me tell you what he couldn't get. He couldn't get this -1. You can try it, okay? I encourage you to try it. Just use 2 processes, derive as what we discussed late on the next few pages. You will get a formula, all right? But you cannot get this -1. So I think after some work, he found he need to propose a 3rd process called stimulated emission, in which an atom is excited. When it is stimulated, it will come down and give out 2 photons of the same frequency, okay? Now, this was not known before Einstein's work. Let's recap what we know from quantum mechanics. Comfortably, we know a formula for absorption and stimulated emission by time-dependent perturbation theory. Somehow, we do not know a formula for spontaneous emission. Einstein's time, these 2 were well known. He proposed this one, okay? So let's get to work. Einstein was trying to establish an equation to describe dynamical equilibrium situation. Namely, at a snapshot, some atoms up there in 2, some atoms at 1. There are EM waves surrounding them, all right? So there is a process, atoms can go up, stimulated absorption. there are two processes atoms can come down. Stimulated emission that he proposed, spontaneous emission that occur naturally. Now, at equilibrium means N2 over N1 is exponential minus h bar omega over kT. Therefore, the situation is that per unit time, there are as many atoms going up as many atoms coming down. One process up, two processes down, but the number must be balanced out. Okay, so do you get the big picture? That is the idea. That's what equilibrium means, right? N1, N2 does not change in time, but they are not different. More down there than up there. Do you get the big picture, guys? Dynamical equilibrium, all right? So let's write it down. We have the big picture. So we are painting the big picture with some mathematics. That's it. So let's get to work. Three processes. Process number one, stimulated absorption, which is from 1 to 2. It is stimulated, therefore, it must be proportional to the EM wave strength surrounding the atoms. That is exactly what our U omega is about, okay? And Einstein started to introduce his A and B coefficients. So this is the famous work of Einstein, the coefficients, A, B coefficients. So he introduced a B coefficient. I label it B12 from 1 to 2. So it is absorption. It is stimulated, therefore, it must be proportional to the strength or the intensity of the EM wave at that particular frequency. Okay, so let me summarize. First thing, probability of absorption per atom per unit time. Einstein write it as an coefficient B12 because it is stimulated. It must be proportional to how much EM wave at that frequency is around. This is called the Einstein B coefficient. So usually at the end, we will skip the labels and just call it the B. But at this point, don't do that, just to remind us what this is, what it means. Now, let's make connection. Using our quantum mechanics, we have derived the transition rate. So this is exactly this. Per unit time is a rate. We only work on one atom. So this is exactly what we have. So this U is this U, and therefore, secretly, we already know what B12 is. From quantum mechanics, this part is Einstein's B12. Of course, we know more than Einstein. Einstein did not know this expression in 1917. There's no quantum mechanics around. Second process, spontaneous emission. Spontaneous means nothing is stimulating it. Therefore, Einstein just introduced his A coefficient. 2, 1 means from the upper 2 to the lower 1. There's no U here because it's spontaneous. Don't need to stimulate it, okay? So this is the probability of spontaneous emission for one atom per unit time. Probability has no unit, one atom has no unit per number, and then it is 1 over time. So this thing has a unit of 1 over time. A and B carry different units. Remark, For quantum mechanics, we don't know what to do with this spontaneous emission term. Stimulated emission, the third process. Just like the stimulated absorption, it must be proportional to how much EM wave at that frequency is around. So it's proportional to U of omega, and Einstein introduced his third coefficient. Because it's also stimulated process, it's use the symbol B, but it is B21. All right. Now, I hinted one more time here that without this new process proposed by Einstein, he could not get the Planck's formula, that -1. Let's see what do we know in quantum mechanics. In quantum mechanics, we have an expression for B21 because we have lambda 21. We also know more. We know that this thing is the same as B12 because we have derived the formula lambda 12 is lambda 21. Okay? Einstein didn't know that, of course. So let's set up the stage. Dynamical equilibrium. We have one process for atoms to go up there, two processes for atoms to go down to 1. Per unit time, some atoms go up, some atoms come down. But to keep the ratio a constant, which is just temperature dependence, the number going up must be equal to the number coming down. All right, so let's do that. There's only one process for atoms to go up. So how many of them from 1 to 2 per unit time? That is absorption, right? So we have per atom, this is the probability of stimulated absorption. We have N1 in the lower level 1, therefore per unit time, that many atoms will go from 1 to 2. There are two processes for atoms to go down from 2 to 1. One is a spontaneous emission. A21 is per atom per unit time. I have N2 up there, therefore this many will be coming down by spontaneous emission. Similarly, this many will be coming down by stimulated emission, new process proposed by Einstein. Because the system is at equilibrium, dynamical equilibrium means this two coming down, coming up, going up, coming down must balance. Therefore, you can keep the N2 over N1 at the same ratio all the time. So therefore, we have this equal sign, all right? So this is what Einstein did. So do you understand, guys? Einstein didn't need 4 dimensions, things like that, to do good physics. This is very simple but insightful physics. Get that? Now, this is dynamical equilibrium. But don't forget, we have one little piece of statistical physics. N2 over N1 equals this. Okay? Now, let's sit down to work. From this line, we can solve for the ratio N2 divided by N1. Right? You factorize N2 out, divide the whole thing to the other side, divide N1 to this side. So you get this. Okay? So this highlighted box is obtained from equation 30. Okay? But now, statistical physics say this ratio is also this. Therefore, dynamical equilibrium, statistical physics give us this. Therefore, we can solve for an expression for the light distribution, the strength of light at a particular frequency is given by that. Now, I hope that you started to see that started to look like Planck's formula, and you have B12, and it is this B21 stimulated emission that gets into this place. If you don't have this term, you will never get this -1 in the denominator, you see? Okay, so this is what we can get up to now. So Einstein want to get at Planck's formula. So it's like in exam questions, when you are asked to show something, you can always show that, right? Somehow you make two mistakes in the middle, at the end, you always say, I show that. So this is the same game. So this is the answer. And this is what we got up to now. The question is, how can we get this to become this answer? What do we need? So in order to get Planck's formula, the Einstein coefficients obey some relationship. First of all, we need B12 equals B21. Once you have this, you can factorize the B12 out and you get this denominator. Okay, now this is very difficult to do. Einstein need to introduce a new process and then summarizing the requirement as B12 equals B21. We are not surprised because we already derived this relationship using quantum mechanics. So, good. Things are connected. Well, this is about 10 years later, right? This is a quantum mechanics, 1926, 27 or so, Dirac's work. Secondly, once you put this to be the same and factorizing it out, you have this ratio in front, and this ratio must be equal to this in order to get the Planck's formula. Therefore, we got what we want to get. We found that A over B must be this prefactor in Planck's formula. Therefore, we obtained a relationship between A and B coefficient. In quantum mechanics, we know this. We don't know this. But now Einstein said they are related, but with an important prefactor, especially this omega cube factor in front. The other are some kind of constants. Speed of light, Planck and pi, Planck constant and pi. Okay, so this equation is what we are sorting for. Okay, we are looking for. So that's the end of Einstein's work, rather magical, I would say. Somehow it confirmed 10 years later what quantum mechanics result would get, and also provide a way to get at spontaneous emission probability without any further effort. We just plug our answer here, we get a formula for A. Okay, now the rest of this discussion has to do with the meaning of Einstein's formula, the meaning of the results. First thing, we see that there is an omega cube extra factor times B. Now, yes, there's a question about can we extend the discussion to more than 2 levels, but actually The yes means you can arbitrarily set your omega. We are not assuming a particular omega in the whole argument. So this time you discuss this omega, next time you discuss this omega, next time you discuss that omega, and you get the whole black body formula curve. Okay? Now, this, we already have a formula for that, and then we know A is now having an extra omega cube factor. Now, that is an important implication. It means, now this is the ground state, this is a first excited state and a second excited state, a third excited state, and so on. Okay? Now, let's say this state could decay to the ground state. As a more highly excited state will have a bigger omega. Okay? And therefore, it means the spontaneous emission rate will be bigger. That is to say, easier to decay. Okay? It means this excited state higher in energy to the state that it will go down is less stable. Okay? Or shorter lifetime. All right, so that is an important idea with this extra omega cube. And lifetime is rather obvious because A is probability per atom per time. So it has the unit of 1 over time per time. You flip it, 1 over A is a time. So later on, we will see that defines the lifetime of an excited state. It is related to spontaneous emission rather than stimulated emission. And this is optional, okay? I already mentioned it. This omega cube term actually has two sources, h bar omega, a photon energy, and this omega square you will see later on in counting the density of states in your statistical physics course. So we have suddenly, without doing anything actually, well, we have done something. We went back in time to go back to Einstein's work and come back to quantum mechanics. So with this factor times B, we call that, we have the quantum mechanics transition rate, stimulated processes. We have this B, Einstein's B times the U. So this is our B, well, Einstein's B. And we know that multiplying this factor in front times the B is the A. So suddenly we have a result, quantum mechanical, for spontaneous emission per unit time. So this is the 1 over time quantity, okay? And then suddenly we also got a lot of results, right? First of all, there are selection rules. Same integral, spatial integral, initial final, the electric dipole, the R in between. So that also follows the same selection rules. Of course, this answer is based on electric dipole mechanism. And then we have this omega cube and a trunk of constants. I highlighted all the important things using a different color, all right? Now this, together, this is the electric dipole mu square. And flipping this will be some lifetime. Therefore, the lifetime of an excited state is now something that can be calculated quantum mechanically. I want you to appreciate that this point. Many of you learn quantum mechanics as a chunk of symbols, Hamiltonian, operator, Hermitian, orthogonal, all that kind of fancy things. No, quantum mechanics is very practical and quantitative. If you plug in everything and calculate it, you get a number for the lifetime of an excited state. The experimentalists can measure the spectral line. If the resolution is good, there is a line shape. How sharp is that line? The line shape, there's a width. The width can tell us the lifetime of the excited state. Experimentalists, theorists, quantum mechanics, they could compare results. And usually quantum mechanics works very well. All right, now you should appreciate this point. Instead of thinking in terms of a Maxwell equations, all symbols, a Schrödinger equation, all symbols, the more symbols, the happier you are. That is not the way to do physics, okay? So at this point, let us take a short break. Then I will move on to define the lifetime of an excited state. And then we will have a brief discussion on laser physics.